Okay. Now, what happens if we have now a dynamic setting? So imagine that you did a certain distribution over the cloud. And then you find out, oops, here, suddenly I have 4x, all the others have x megabit per second, and now 4 times and 3 times. So you should shift the behavior. You should go to one cloud and say, give me your stuff and bring it over here. How can you do that? It's the same problem. In RLNC and others, you have to make a fuss about it and say, everybody comes here, I need a new situation. In network coding, you just ask the others, whoever has time, send me packets. And I put them in, I recode them into my system, and whenever this is delay tolerant, it's not so much that you have to ask all the pieces and then have a big chunk in your memory to do something, very little operations over here, and then you can adapt it. Also, that we did, you look here at the time taken for a download, and these are the 5 clouds. And this is a distribution. The red was dominating, a little bit of green, way more blue, big on yellow, and very small on the greenish, bluish, whatever color this is, right? And suddenly you see something happened here, right? Here, the red one did not perform. So the others had to do something, and they exchanged packets to each other to help each other, and you see that it went up a little bit, and then it came down. And when this red came back, they just killed the amount of packets they had because they knew the red one is coming back. So this is quite interesting in dynamically shifting the amount of data you have there. Now, here's another example. If you have this information given in, let's say, 20 small pieces, right? And we have containers of size 4. So here you have 10 containers of size 4, which gives you 40 pieces for storage, and you have 20 original data. What can you do? You can store the data twice and say, I have a replication code. Or you code it systematically until 5 and then make coded packets down here. Reed-Solomon. Or you may take Reed-Solomon over all 10. Even this is possible. Or you use RLNC over all 10, as you like. Now the game works like this. What happens if you kill 3 of these buckets, and because they're not there, you give the system 3 empty buckets and say, please fill them up. And then we look into this, how can we fill this up? So we call them parents. In order to replace this, we need 5 parents. Whatever is remaining out of the 7, but 5 parents have to come here, and then I can decode when I have a Reed-Solomon code. If I have an uncoded system, I just have to go 3 plus 5 to the 8. Are you available? Just make a copy. This is better, right? Just a copy is better. But if I hit twice this one, I lose the data. I lost the data integrity right away. With the code, it's harder to do that. Then is also the question, how much parents can you really get? So what happens if this guy, in the Reed-Solomon case, and not systematically, but he will say, I have coded everything Reed-Solomon, and I only get 4 parents. But he needs 5 to decode. What can he do with this? Nothing. He doesn't have to throw away everything. He can pick one of them and just copy it here. So you get a copy of a copy. You degenerate the system. You're moving towards an uncoded system, so to speak. You get duplicates. Yeah, maybe you can repair it later if you want, but when you have network coding, it doesn't matter. You get 4, you recode 4. You get 3, you recode 3. As long as you get 2, there must be an advantage. So, can I do, it works automatically, Frank. So, let's see here. This is a tool we made ourselves. So you say, how many clouds you have? 10. Number of storage per cloud, 4. Do you use network coding? How many symbols? Field size, symbol size, how many rounds? Shootout, 3. Fast recording, alpha, there are some things. Number of parents, 5. So this is your original system. and the red ones are the shoot it out. And he said, okay, let me see that, what happened. And what you will actually see is who is feeding who, right? How much data is there? How much do you move around? And how is the system performance? And he says, finish, running, finish, success. So after 100 rounds, per round I'm killing 3 of them, everything was okay, right? And with that, we said, okay, then let's make these ice cubes, right? I showed you the ice cubes in the beginning. Now we're coming to the ice cubes. Now I show you 6, not only 3. And the first column here is no coding. And I want to see what is the storage that I need and what is the traffic. So of course I can say if I have the 20 pieces, I don't want to duplicate it only twice. Maybe 5 times, 6 times, 10 times, right? But this is cost. This is money, dollar. The more you go here, the more you have to pay. In traffic, the same. The more you go here, the more you have to pay. And then the reliability, you want to be on top of the ice cube. As long as you're on the plateau and you don't fall into the mountain, so to speak, then everything is fine. And here we have no coding. Here we use Reed-Solomon, and here we use network coding. And then we have 2 of them. This is the fully distributed policy. We don't know what happened. Totally chaos. And here is Genie. You are God. Imagine you have an SDN controller that can tell you exactly what happens. So what can you do with that? You can prevent certain situations. So imagine you have a Reed-Solomon, only 4 parents can reach you. You don't copy maybe this one that you have already copied 2 times. Maybe you copy another one to keep the system alive. You can make way better decisions. Okay? So let's have a look at this. So once again, this is no coding, Reed-Solomon, and network coding. You have to be on top of the plateau to get data integrity, and you want to be as close as possible to the point down here, 0, 0, in storage and traffic. I could not pause this. No, it's an animated GIF, unfortunately. So unfortunately not. But what you see here is no coding is not a good idea, right? Even if you have the Genie policy, you can prevent something, and this is not nicely simulated, I have to say. We are currently doing this in a way better way. So if you see the blue icebergs, everything is fine, right? Then in the back, you can do something over here, right? Now, this is because you can plan, God's plan, right? This is Reed-Solomon, and you see that this breaks down. It needs some coordination. You will see it later on. So here, it breaks down quickly, but it's melting from the side. So if you just do replications of the code or more redundancy, then you can save you towards the end. Here you can see you have different working points. So either more storage or more traffic. Somewhere, if you're here, everything is fine. So now look at these 2 ice cubes. What is the difference between them? So first of all, you see it's way better than everything that we have seen before. But what you also see is there's no difference whether I have the full control what happens in the system or the full information, or I just do it distributed without knowing what the others are doing. Does it ring a bell? What have you seen in transport where this was more or less the same? You remember the relays that we had? The relays were just taking in information, recoding, sending out, without organizing themselves. This was optimal. It's the same what happens here. So I don't want to claim how much this is better than the others. That you can see by yourself. What I find very interesting is this one. First I thought, did they give me the same video, until you see some small things where they differ, right? And this means that shows the power of the code. We have random coefficients. We don't plan. Because no plan survives the contact with the enemy, which is reality. So you cannot plan for something if you don't know what happens. If you know what would happen, then you could do something better here, for sure. But you don't know it. So to show you the gain, what you can see here, this is the reconstructed traffic over the storage. And then you see decentralized Reed-Solomon, centralized Reed-Solomon. Centralized, so controllable replication. And this is RLNC. So even with full information for the others, this is still an area where you gain. Okay? So you will gain either in storage or in traffic or in both, depending on which blue point you are selecting here. And just to show you this is the ice cube again. Here is the round number. And you see this is the green one is the actual cost function, what you can choose, and the red is the theoretical one. So you see now the rounds are counting, right? Which means we are killing some of the places, and then something will come to repair. And with these counters of rounds, you see the green one is coming closer to the red one, right? And you would expect this to be exactly on the red one, but as we have some granularity here in the storage, we will be sometimes below the red one, right? So of course, if you're here, the next one is here. Here it might be staying here, but there he has to go behind the. If you do more, I think he will go below this point. But you need more stuff. Now, what we have shown you now is transportation. We have shown you storage. What remains for research is now computation. So there's something called the mobile edge cloud, which is a computing entity that you would like to use in order to reduce latency. So if you want to steer a car and the car is moving, you would like to move the software as close to the car as possible so that they can communicate quite quickly. So the concept is like this. You have one big data center over here. He's computing something and then sending the data to a car that goes down here. But because of this latency of this communication path, it's better to move the software down here in a very elegant way. So you need software. There's something called software-defined network function virtualization. Wherever the robot or the car is moving, we are moving the software. Now, we know how to make this dual transportation over there. We know even how to bring the storage there now. How to do computation here is still a matter of research. Maybe next semester, the semester afterwards, we can tell you even how we managed to do that. That is a little bit the remaining research stuff that we are doing, understanding how to really distribute the computing over these base stations. But it looks quite good that we can present something next year. I hope so.